All right, now we're going to apply that, as I said, to actually predicting what traits are going to be passed on from one generation to the next. Now, this is important for not only people that are farmers, like Mendel was, planting plants and trying to get the traits they want. So they would want to know, what parents do I have to put together to get these good traits that I want? Maybe I want corn that has really strong roots so it doesn't get blown over in a windstorm. So what kinds of parents do I have to put together to get this result? But it's also important in humans. For example, a lot of diseases are genetic. We want to know, what is the likelihood if one parent has the disease and one parent doesn't, what's the likelihood they're going to pass on that disease to their offspring? So this predictive value is really important for a lot of real-life scenarios. So we're going to talk about how we can use all this information from meiosis and what Mendel learned to actually predict some outcomes. The tool that we use to make these predictions is called a Punnett Square. Punnett is just the last name of the person who came up with this mathematical tool. And it's simply just this 2x2, in this case, it's going to be a 2x2 grid that helps us to organize these alleles that are going to get crossed in a potential fertilization. So we're going to start out by having two heterozygous parents. You can see right up here the mother is heterozygous and the father is also heterozygous. And we're going to stay with our tall, short phenotypes. So if the mother is heterozygous, she must be tall. And if the father is heterozygous, he is also tall. So our genotypes are big T, little t, or heterozygous. Our phenotypes are tall. We want to know what's the likelihood of them having tall and short offspring. Maybe they're really concerned about having, basketball players in their family or something. They want to have some tall children. They want to know what's the likelihood of having these tall children. All right, so the first thing we do is we start to plug in the information from what the mother is carrying on her chromosomes. Now remember, in meiosis 2, the alleles get separated from each other because the chromosomes are separated from each other. So we're putting the mother's big T allele in a separate separate column, these are columns, in a separate column from the little t allele, because they will get separated. We're going to do the same with the father's alleles. So we're going to put them in separate rows. Father's big T allele and the father's little t allele. Now, when you do this, because you're going to do lots of Punnett squares in class, you do not have to write father's first allele, father's second allele. The only thing you'll have to write is big T, little t, whatever the allele happens to be. So I'm just going to go over that with those alleles. But it's important that each allele gets its own row or column because that signifies how they get separated during meiosis 2. Then we use our little tool, our grid, to actually fill in the empty spaces. So this big T allele right here and this big T allele right here are going to come together in this box. Okay, it's kind of like Battleship if you ever played it. Okay, you line up the rows and columns to where they match. This box represents this little t here, and then this this big T here from this row. So that would go here. This box down here is the big T from up above and the little t from the side. And this box right here is the little t from up above and the little t from the side. So that's how we fill in the grid. I'm going to take you through that one more time to show you exactly again what's going on. So big T, you can see the red big T allele came from the top and the blue T allele came from the left. Big T, little t, father's big T, mother's red T, big T, little t, big T from the mother, little t from the father, and then little t, one from each of the parents again. So that's how we fill in those boxes. Now, what do those boxes represent? Well, essentially, each of these alleles is carried in an egg from the mother. These are eggs. And from the father, these alleles represent the sperm, right? Because they are what's carrying the chromosomes. And when we fill in these boxes, each of these boxes here represent one egg and one sperm coming together. So that must mean that these are fertilization. And when the egg and the sperm come together in a fertilization event, we call that resulting structure a zygote. So these are the 4 possible zygotes, or the 4 possible results of fertilization. Okay. Now, does this mean if 4 eggs are fertilized by 4 sperm, 1 is going to look like this, 2 are going to look like this, and 1 is going to look like this? No, that does not mean that. It means the odds are that 1 is going to look like this, 2 will look like this, and 1 will look like this. But just like when you flip a penny 10 times, it's not exactly 50-50 heads and tails. Okay? It's random how they're going to end up being. So you could have 8 heads and 2 tails. The likelihood is it's going to be 50-50, but it isn't always. Same with this. Okay, the likelihood is that we're only going to have 1 out of 4 chance of getting 2 little t's together in fertilization. 1 little t from the sperm and 1 little t from an egg. But it could happen more or less depending on the randomness involved. The last thing I want to do with this is use our words that we just talked about, which is genotype and phenotype. We're going to take those words and we're going to calculate what are called the frequencies. See that word down here? The frequency, or in other words, the chance, the likelihood of certain genotypes and phenotypes showing up. Okay, so first we'll do the genotypes. So that's pretty straightforward. So genotypes, remember, are the allele combinations, and we just, again, figure out our percentage, or our chance that that's going to happen. As I said, only one of these boxes has big T, big T. So we have a 1 out of 4, or a 25%, oops, back up. A 1 out of 4, or a 25% chance of big T, big T. We have a 2 out of 4, or a 50% chance of big T, little t. And then again, we have a 1 out of 4, or a 25% chance of little t, little t. So that is our genotypic frequency. So if this mother and this father have children together, these are the chances that they'll get these combinations in their offspring, in their children. Now let's look at the phenotypes. Remember, phenotype is the outward outcome of those alleles getting together. So let's take a look at what they actually look like. Remember, we said tall was dominant and short was recessive. So this guy has 2 dominant talls together. So this potential offspring is tall. So we got 1 tall. These 2 have a tall with a short, but remember the tall is dominant, so it covers up that recessive short allele. So these guys are also tall. The last one has 2 little t's, so it has 2 recessive alleles together, 2 shorts, short, short, so this offspring has the potential to be short. So again, we count them up the same way as we did before. Again, this is our phenotypic frequency, what they look like. 1, 2, 3 out of the 4 are tall. 3 out of 4 is 75%. So there's a 75% chance that their offspring will be tall. 1 out of the 4 is short, so there's a 25% chance that the offspring will be short. So we've got the phenotypic frequency is a 75-25 frequency. And if you remember back when we did the genotypic frequency, it was a 25-50-25 frequency. So the genotypic and the phenotypic frequencies aren't always the same because the alleles that you have don't always automatically equal the same phenotypes because that dominant allele can cover up that recessive phenotype. You're going to practice some of these Punnett squares in your assignment that you're going to do after this vodcast. So you might see this particular cross again, so you can use this as an example as you're doing your assignment if you don't remember how to do it. But then there'll be some other crosses with different alleles, so different combinations of letters, and in all the cases you'll have to come up with these phenotypic and genotypic frequencies. What are the likelihood that certain alleles or certain traits will be passed on to the offspring?